Howdy. Citate daily. The hottest rock on Earth. Record high proven by researchers. Postdoctoral student Gavin Dolometti finds new evidence proving record high for rock on Earth. If there was ever any doubt that the 2011 discovery by a postdoctoral student was indeed the hottest rock on Earth, new findings from a Western University led team of researchers are putting that uncertainty to rest. 11 years after researchers from Western unearthed what was then perceived as the hottest rock on Earth, a recent study found 4 additional zircon grains, a hard mineral commonly known as a substitute for diamonds, that confirmed the previous rock's record high temperature of 2,370 degrees Celsius. This is how it looks, obviously. Whatever this picture means. Oh, too much cacao. The study, published in the journal Earth and Planetary Science Letters, was led by Earth scientists, postdoctoral student Gavin Dolometti, and co-authors Timmons Erickson from NASA Johnson Space Center, Gordon Osinski, and Catherine Naish from the Department of Earth Sciences, and Karen Cyril from the Laboratory of Thermomechanical Metallurgy. In 2011, then PhD student Michael Zanetti has working with Osinski at the Mistastin Lake impact crater in Labrador, when he found a glass rock that contained small zircon grains frozen inside it. Frozen. That rock was later analyzed and found to have been formed at 2,370 degrees Celsius temperature as a result of an asteroid impact. These findings were shared in a study published in 2017. Discovery Hill, Horseshoe Island, Impact Melt, Zircon Grain Locations. That's the crater. Some few hours ago, I've been watching with a big smile a video from See the Pattern channel, and I just wanted to share you a quick glance into it. Glimpse? Probably. Check it out. He's better in talking and knows about stuff. Check it out.
He performed experiments to show the similarities between the electrical craters and those found on the moon. Many decades later, Tara Desai and her colleagues would experiment using lasers fired onto a metal plate. These produced similar indent craters, but also much more complex versions with a cone in the center. Analysis of the shape of the craters showed that they were similar in shape and contour to the example craters. What is rather intriguing about this work is that a laser is essentially an electromagnetic pulse. Normally, electrical breakdown occurs when there is a sufficiently high electric field strength in an insulating medium, like air. We will go into more detail about this in a future video. Once this occurs, an avalanche process can start, which forms a plasma which can become the conducting path. But this breakdown process can also be initiated by an intense laser pulse. The process is somewhat different, as it does not require a potential difference to be initiated. In the experiments, they were attempting to demonstrate the similarities between craters formed through lasers and those found naturally. From the report, it would appear that this seemed to be limited to simply showing how they were able to form simple bowl-shaped craters, but also craters with a central peak. The main aim was to try and show that a similar mechanism could be used to explain all types of craters. Both Ford and Desai's work were based on creating craters on a metal surface, which is not really representative of most planetary bodies. C.J. Ransom expanded on these experiments by using materials that are found on planetary bodies, such as sandstone, barium carbonate powder, and aluminium hydrate powder. He has written a number of papers, some in conjunction with Wal Thornhill, about the results of his experiments. he was able to demonstrate an extensive range of features found with a range of plasma and sample conditions. These included crown-like features, rimless circular and non-circular craters, crater fields, multi-ring craters, and a variety of Lichtenberg discharge patterns. Sometime later, Billy Elverton started experiments examining electrical discharges on surface formation. In particular, one aspect he focused on was what would happen to the particles in an electric field as well as a discharge. He also showed evidence of crater formation as well as demonstrating the effects that the field would have on the smaller particles and how this could be responsible for many other features, not just craters, including the carving of plains, valleys, the formation of ridges, and mountain-like structures. What both C.J. Ransom and Billy Elverton showed was that the material used as the surface made a huge difference to the types of patterns observed. One interesting aspect of Billy's work is that in some cases he used an AC power supply, but in others used a rectifier to turn it back to DC. When either the anode or cathode were used above or below the surface, he noticed the same pattern whether using AC or DC. More recently, both Electric Universe Eyes and Ben Hyde have continued some of these experiments to examine the effects of electrical discharge on solid rock, sand, or other particles, looking in particular at electric geology, which Billy had initially touched upon. There are also a variety of other experiments conducted using plasma, which were examining the damage that can be caused during certain experiments. These also demonstrate similar scarring effects on either the anode or the cathode. In the next episodes, I want to examine different types of craters or scarring formations and try and explain how these could have been created using a discharge.
So now, I recommend you to watch the video. I mean, this whole and all the others he put out. He's really good at doing videos and explaining things. See the pattern. Open your eyes. Wake up. Everybody wants to go to heaven. No one wants to die. This is like propagating free speech, but still not thinking for yourself. So, probably first better start thinking for oneself. That's a good place to start. Thanks. Bye.